Okay, so welcome back students. So in the last class we did something related to matrix. So diagonalization and all these things are there. Today we will do something which is called rank of a matrix. It is a very important concept, rank of a matrix, but before going to the definition and all these things, I like to introduce few other things related to the rank of a matrix. So first one is row and column vectors. Now what is this row and column vectors? Let us suppose a matrix is defined, say n by n matrix is defined as A11, A12, A1n, A21, A22, A2n, AN1, ANn. Now this matrix contain different rows and columns. If I take individually each row or each column, they will form a matrix. So that is nothing but the row and column matrix. For example, if I take the column C1 in our standard matrix notation, standard vector notation rather. So this C1 in n tuple form can be represented at A11, A21, A23, A31, AN1, like this. In a similar way, I can write the init. So here A is represented by this 1 1. First one is for the row and second one is for the column. This is the first row, that is why this is 1, this is the second column, that is 2, that is the standard way we define a matrix. So the ith column, that means this one, if I write in this way in tuple form, then it will be the column vector. This is a column vector. So general column vector is nothing but A1i, A2i and A ni. This is the ith column vector. In the similar way, if I write the row, then I can write the row in this way also. So this is the row vector. This is the row vector defined by R. 1 is the first row, that means this one I like to write, and if I write, it will be something like A11, A12, A1n in n tuple form. In a similar way, if I write the ith row, it will be something like AI1, AI2, AIN. So I have a matrix and this matrix has this form, and if I take the row individually, then I will have a individual column vectors. These column vectors are here, and also I can write these rows into vectors, and these are here. These are called column vectors and these are called row vectors. It is important in understanding the rank of a matrix, but before that I need to define this row and column vectors in this way. Okay. After that, I will define another thing. Again, a matrix is defined, say a 3 by 3 matrix is defined like this. One two 1 3, A21, A22, A23, A31, A32, A33. So, now we are going to define something called the submatrices. For example, this matrix contain few square submatrices. So, submatrix. What is submatrix? So, this is a matrix, but you can find that these can form individual matrix, we call it submatrix. In the similar way, this can also form a submatrix. In the similar way, this can also form a submatrix, and so on. So, that means there are many submatrix one can form from a given matrix, and these submatrix are important also in understanding the rank of a matrix. So, for example, if I have a matrix A, say I have 2 1 0 minus 1 2 1 1 minus 1 0. Suppose this is a matrix I have. Now, if I write the submatrix, I can write one submatrix like this. This is a square submatrix, mind it. I am just talking about the square submatrix, but there are also some column matrix and row matrix that is associated with this matrix, also they are called the submatrix. But right now I am not bothering about those matrix which are not square, but only those matrix which are square. So, this is one submatrix, square submatrix, then 1 0 2 1. First one I am taking these elements. So, I am having one submatrix like this, second one I am having this, and so on. You can generate many submatrix by decomposing this given matrix A. So, after having the knowledge of submatrix and the row and column vector, then we are in a position to understand the rank of a matrix. Okay. So, let me define what is the meaning of a rank of a matrix and what is the physical aspects of these things. So, first thing is that a non-zero real number R is said to be the rank of a matrix So, a non-zero real number R is said to be the rank of a matrix. It should follow few properties. So, one is that all square submatrix of order R is non-singular. And secondly, but all square submatrix of order greater than R is singular. What is the meaning of that? It is not the definition is something like that, but in order to understand that, we need to find out what is the meaning of non-singular and singular. So, I believe all of you are aware of these things non-singular. The meaning of non-singular means that the determinant of the matrix is not 0 and singular is the determinant of the matrix is 0. That is one definition. Other way you can say that there is no unique inverse exist for singular matrix, but in non-singular matrix you can have the inverse of that. But we should now remember only the thing that non-singular means the determinant has to be non-zero. So, what is the meaning that all square submatrix. So, first I need to find out what is the submatrix and then find out a order R for which this is non-singular, and also that the all higher order R, if I try to find out the determinant of that matrix formed which is the order of greater than R, then the determinant of that matrix should be 0. So, let us do one example that might be easier to understand the rank of a matrix. So, you should example. Say a matrix 2 1 0 minus 1 0 1 1 say minus 1 say 1, something like that. So, this is a matrix given and we need to find out that what is the maximum order of submatrix which is non-singular. So, first please remember, let me try with this matrix, this submatrix. If I take this submatrix and try to find out the determinant of these things, I will readily find that the determinant is 1 which is non-zero. So, this is a submatrix of order 2. So, here R is order 2. If R is order 2 here, that means readily I can say that the rank of a matrix is 2 because it is non-singular, but please hold on, this is the first condition that it is satisfying by this. At least one matrix should be non-zero. If one submatrix is non-zero, then readily I can say that the rank should be at least 2, but this matrix, if I write this matrix in the whole matrix, it is also a submatrix of the given matrix. So, it is not that I can only call this is a sub square matrix, the whole matrix is also some sort of submatrix of the given matrix. So, that means I need to check whether this matrix itself is non-singular or singular. That means I need to find out the determinant, that is all. If I do that, let me do and try to find out what is happening here. So, 2 0 plus 1 multiplied this and this, it is 0, and then minus of minus 1 1, it is plus, then plus 1 this and this. So, 1 into 1, so I will have 1 minus 0, and finally plus 1 this one. So, 1 into 1 and 0. So, it is again 1. So, if I do, then I will find that it is 2 plus 1 plus 1. So, it is coming out to be 4, which is non-zero, That means first, before doing the submatrix like order less than the order of the matrix, first we need to find out the determinant of the matrix itself and need to find out whether it is non-zero or not. If it is non-zero, then readily I can say that the rank of the matrix A is 3, or rank A is 3. Okay. So, a matrix is given, first I check the determinant whether the determinant is non-zero or not. Once you get the determinant non-zero, then readily you can say the rank of a matrix 3, you do not need to do anything. But if the determinant is 0, then you need to go to the other sub matrices which is the order less than R. So, here from the very beginning I find that the rank is 3. So, let us go to another example. Let us go back to another example. Say A is 1 minus 1 0, say 1 3 minus 1 and 2 minus 2 0. It is something this is the matrix I have. So, first I need to check whether the determinant of this matrix is 0 or not. If the determinant is non-zero, then readily I can say this is a 3 by 3 matrix. So, readily I can say that the rank of this matrix is 3. So, now first the determinant 1 1 2 minus 1 3 minus 2 0 minus 1 0. If I do, then I will find that 1 3 into 0 0 minus 2 this into this, then minus 1 then I am going to this. So, this cut, then this. So, minus 1 should be plus 1. So, I will cut this row and this column, then I will have so let me check once again. I will have this I will have this cut and this cut. So, 0 into 0. So, 0 minus 2. So, it will be plus 2 and then plus 0 into something which is 0. So, please check, I take this one, this into this into this, here 3 into 0 0, then minus 1 into minus 2 which is 2 minus 2, then I take with a negative sign. So, it will come to a positive. So, I will multiply 1 into 0 and minus 1 into 2, 1 into 0 0, minus 1 into 2 is minus 2, but there should be a negative sign. So, this negative sign make it plus, and finally 0 into something which is, since the 0 is sitting here, I am doing this way. Anyway, you can do the normal way also by doing this. So, here I can see it is minus 2 plus 2 plus 0 which is 0. That means this matrix is singular, but my definition suggests that the matrix should have at least one non-singular matrix, submatrix with order R, but here the order R means order 3. So, third order matrix is 0, that means the rank should be the rank of the matrix obviously less than 3, obviously less than 3. So, next we need to find out whether any of the submatrices are non-singular or not. So, let us try the first one. So, first one, the submatrix is 1 1 minus 1 3 minus 1 3. So, readily I can find that it is 3 plus 1 which is 4, which is not equal to 0. That means the submatrix is a non-singular matrix of order 2. So, readily I can say rank of A given matrix is equal to 2. Okay. So, this is a standard way to find out what is the rank of a matrix. So, the recipe is something like that. A matrix A is given to you. When the matrix A is given to you, if it is a 3 by 3 matrix, then first you need to find out the determinant of this matrix. If the determinant is 0, then readily you can understand the rank of this matrix should be less than 3. If the determinant is not equal to 0, the rank of matrix is equal to the order of the matrix. In this case, it is 3, and then you gradually you need to go to the submatrices and find out how the rank is defined. Okay, let me take another example. Let me take another example. Say 1 minus 1 0, 2 minus 2 0, and 3 minus 3 0. If I take this matrix, what happened? So, first the determinant. So, determinant I can readily understand that the determinant will going to vanish if I take this row. So, determinant is 0. So, date of this matrix is 0, that means the rank of this matrix should be less than 3, that is for sure. Now, I am going to take the submatrices. If I take these submatrices, what will happen? 2 into minus 1 minus 2 minus 2 into 2 this plus 2. So, it will going to vanish. If I take this one, it is also going to vanish. If I take this one, so any whatever the submatrix you imagine, if you take that and try to find out the determinant of that matrix, you will find that it is 0, any 2 by 2 submatrix. So, that means here rank of A is even less than 2. So, what is the rank of this matrix? Now, the only element here is 1. So, all the submatrix, if I take the individual one as a submatrix, this is a 1 by 1 matrix or this is a scalar, if it is 1, then the rank of a matrix here is 1. Now, why the rank is reducing like this? Now, you need to understand is in more physical way. So, let us try to find out in terms of row and column matrices. So, now I know that how a matrix can be calculated in terms of its rank. So, in order to find out the rank, how we should calculate the thing, and now I like to introduce the row and column concept. So, another definition which is more important definition. So, rank of a matrix is equal to the maximum number of row or column vectors, which is a very important definition, that the rank of a matrix is nothing but the maximum number of, okay, let me write the now, linearly independent row or column vectors. So, the maximum number of linearly independent row and column vectors is nothing but the rank of a matrix. So, let us go back to some example. So, if I write 1 2 1 0 1 1 minus 1 0 1, here the row and column matrix, if I first I need to calculate the determinant. So, what is the row matrix here? So, say column matrix here is 1 2 1, column matrix 2 here is 0 1 1, column matrix 3 here is minus 1 0 1. These 3 matrix I know. Now, if I calculate and try to find out whether these 3 matrices are linearly independent or not, then essentially what we are doing, we are taking the determinant of this quantity, because C1 of this matrix plus C2 of this matrix plus C3 of this matrix has to be like this. This equation I can write in more so this into this, this into this, this into this first equation, this into this, this into this, this into this second equation and third equation. There are 3 equations are hidden in this form. So, I can write in a compact way and it is right hand side. So, this is nothing but a set of homogeneous equation. So, now in order to find that whether I can have a non-trivial solution or not, I need to figure out whether the determinant of this quantity is 0 or non-zero. If the determinant of these things is 0, say this is a matrix A, if date of A is 0, then we can say, if the date of A is 0, then we can say that I can't have any non-trivial solution. So, trivial solution will be C1 is equal to C2 is equal to C3 is sorry, if the date is not equal to 0, then I will have this quantity, that for non-trivial solution determinant not equal to 0 ensures that you have a trivial solution, and this trivial solution is this. This essentially means that the matrix, that the vectors are linearly independent to each other. So, that means if I take the determinant of these things and find that, okay, let me try to find out the determinant of this matrix A. So, what is the determinant? So, 1 into 1 into 1 minus 0, 0 is there. So, minus 1, 2 into 1, 2 minus 1. So, I have 1 minus, I have 1 minus 1. So, here let me try to do once again. So, ensure that I am not taking any mistake, doing any mistake. So, 1 this into this into this is 1, 0 is not there, minus 1 if I calculate, then 2 into 1 is 2 and minus 1 is minus 1. With a negative sign I can have 1. So, 1 minus 1. So, I find that it is 0. So, that means there should be some trivial solution associated with that. So, that means the rank of a matrix is not equal to the order of this or less than that. So, now I will take another example which will be easier. So, A, say 1 minus 1 0 3 2 1 and 2 minus 2 0. Now, if I look, please look one thing here, that this column vector and this column vector are linearly dependent to each other. That means, if I write this is C1 and if I write this is C2, then I can write C1 and C2 in this way. C1 multiplied by 2 is nothing but C2. That means, these two are linearly independent, are not linearly independent to each other, they are linearly dependent. When they are linearly dependent, that means linearly independent number of rows, number of column vectors are not 3 but 2. So, the matrix has to be, the rank of this matrix has to be of the order of 2, not the 3. I can check also with this, I can check also. So, date of A, if I calculate date of A first and check if it is 0 or not, then readily I find that 1 multiplied by 2 into 0, which is 0, minus it will be plus 2 into 1, it is 2. Then minus of 3, this one, or I can start from here also. So, only just check whether I, so let me do this, it will be easier because there are 2 zeros are already sitting here. So, I need to find out minus 1 into in this column. So, it will be minus 2 minus of minus 2. So, it is 0. If you use this, and calculate the determinant, you will find the determinant of A is easily 0. So, that means this matrix has rank less than 3. So, now you need to find out the submatrix. So, this is the submatrix, and this submatrix readily suggests 1 3 minus 1 2. This submatrix readily suggests it is 2 plus 3 5, which is not equal to 0. That means rank of this matrix A is equal to 2. What is this number 2? This 2 is the maximum. This is the maximum linearly independent, in this case column vector of the matrix. So, that means once the matrix is there, you can inspect and find out whether it is linearly dependent or not. If the two row or column matrix are linearly dependent, then you can say the matrix is not 3, the rank of the matrix is not 3, but less than that, and with that you can calculate with this submatrix formula, you can also cross verify and calculate the rank of a matrix. So, the take away lesson is that rank of a matrix is the maximum number of linearly independent column or row vector that is existing in a given matrix. So, with that note, today we will like to conclude this class. In the next class, we will also calculate something related to matrix, which is important and which is called the Cayley-Hamilton theory. So, with that let us conclude here. So, see you in the next class with Cayley-Hamilton theory. Thank you.